How to estimate limit at a point. Let's see what happens on the y-axis as we approach c on the x-axis. We're choosing closer and closer values each time. And as you see, we get closer and closer values to a certain unique value on the y-axis as well. Let's see from the other side. Similarly, we choose closer and closer values to c on the x-axis. And we are getting closer and closer values to a certain value L on the y-axis. So we can say, if fx approaches a unique value L as x approaches c, then the limit of fx as x approaches c is L. Again, as we approach c on the x-axis, our function approaches L on the y-axis. And the notation is the limit of fx as x approaches c equals L. Now let's see our first example. Estimate the limit of negative 3x plus 1 as x approaches 2 using a graph. Support your conjecture using table of values. So let's see what happens as we are approaching number 2 on the x-axis. We're approaching it from both sides. And as you can see, there is one certain point that we're getting closer on the y-axis, and that point is negative 5. So we can say that the limit of negative 3x plus 1 as x approaches 2 equals negative 5. Let's see if we can support this conjecture using the table of values. So here is our table. And we need to approach number 2 from the left-hand side. So we're getting smaller numbers than 2, but each time we're getting closer to number 2. So let's say 1.9, 1.99, and 1.999. And now we're going from the other side. So 2.1, an even closer number is 2.01, and closer number 2.001. Now, if we substitute these values into our function, we get the following values. I hope you can all see that we're getting closer to the number negative 5. So it means that our limit is indeed negative 5 as x approaches 2. As you notice, negative 5 is also the function value at point 2, so f2 equals negative 5. This is not always the case. Let's see our second example. In this example, our task is to find the limit of this rational function as x approaches 5. We will support our conjecture using table of values. I hope you remember that whenever you deal with a rational function, you have to find the excluded value. If you put this function into GeoGebra or Desmos, you would get a simple linear graph. But we can see from the function itself that we have an excluded value, and it is 5. So when we draw our function, it will look like this. It will have an empty circle on the value 5, because our function is undefined at point 5. So let's see what happens as we approach number 5 on the x-axis. Well, we can see that the function values will approach number 6 on the y-axis. So we can say that our limit at point 5 equals 6. And we can support our conjecture using the table of values. Here we go. Here are the numbers that I chose on the x-axis. And if we substitute, we will get values for the y-axis. I hope you can see that we are getting closer to number 6, according to the table of values as well. So we can say that our limit at 5 equals 6. So this time, as you can see, the limit as x approaches c was not equal to the function value at c. Seeing our previous two examples, we can say that the limit of a function f(x) as x approaches c does not depend on the value of the function at point c. In the first example, if you remember, the function value at point c was equal to the limit of our function at point c. However, in the second example, the function value at point c was undefined, but still we had an existing limit at point c. And the third case is when we have a limit at point c and we have a function value at point c, but they are not equal to each other. And now it is your time to practice. Use GeoGebra or Desmos to graph the following functions, then find a limit in the given point according to the graph, and then support your conjecture using table of values. Be careful with the trigonometric functions. If you use radians when you graph the function, make sure that you use radians when you fill the table of values. If you use degrees in one case and radians in the other case, you may get different values for the limit. And here are the answers for the first two questions. In this first case, the limit was equal to the value, the function value. In the second case, I had to add this empty circle into my graph, as GeoGebra didn't do it for me. And in the second case, the function value and the limit was not equal. And the answers for the second two. As you can see again, in the first one, the limit and the function value equals. And with the second graph, I had to add the excluded value with an empty circle. So we can see that the function is undefined at point 0. And also the table of values showed the answer. This time the limit and the function value is not equal. In some cases, we can consider the one-sided limits. It means that if x approaches c from the left-hand side and the y values approach to a unique L1 number, then we can call L1 as the left-hand limit of the function. As you see in the notation, the only difference is to put a little negative sign by the value, the c value, and we will call it left-hand limit. Similarly, if x approaches c from the right-hand side and the y values will approach a unique number L2 on the y-axis, we call this L2 value the right-hand limit of the function. The notation is similar, but this time we use a plus sign. Let's see the importance of the one-sided limit. The limit of a function f(x) as x approaches c exists if and only if both sided limits exist and are equal. This means that my two-sided limits only exist if I have both of the one-sided limits and they are equal. Let's see this in practice. This time, our task is to find the one-sided limit and the two-sided limit of a piecewise defined function, which is a linear function below number -2 and a quadratic function above number -2. If we look at the graph, it means that from -∞ to -2 with an open end, we have to use our linear function. And then starting from -2, this is a closed interval, so it means -2 value belongs to the quadratic function. We graph the quadratic function. And now we observe the one-sided limits at first. Let's see what happens from the right-hand side. Here, as we see, as x approaches -2, our y values approach -8. So we can say that the right-hand side, the right-hand limit, is -8. Let's see what happens on the left-hand side. as we approach number -2, our function value will approach +3. So we can say the left-hand limit is +3. So we can see that the two one-sided limits are not equal to each other. This means our two-sided limit does not exist. We have a similar function. It's also a piecewise defined function, and we need to find both the one-sided limit and the two-sided limit. Our first bit is a cubic function, and the second part is a linear function. So here is my graph. Below +1, we graph our cubic function, and starting from +1, we graph our linear function. And now let's see about the limit. The right-hand limit as x approaches to 1, our function values will approach to number 3. And the left-hand limit, here we go, as we approach to +1, the values will approach to +3. So the left-hand limit is also +3. So we can say that the two one-sided limits are equal to each other. So therefore, our two-sided limit is also equal to 3. Now we will need to graph this rational function. I hope you noticed that the excluded value this time is +3. And as we graph the function using GeoGebra or Desmos, we can see that there is an asymptote at number 3. Let's see the one-sided limits first. As we approach number 3 from the right, we can see that our function will increase with no bound. We can also notate this as our right-hand limit equals to infinity. Similarly, for the left-hand side, we can see that our function will decrease with no bounds, which means that we can notate as our left-hand limit at 3 is -infinity. We can also support this with table of values. We can choose approaching numbers from the left and approaching numbers from the right, and then substitute. We can see that from the left, we are getting smaller and smaller numbers, and similarly, from the right, we will get larger and larger numbers. So there is no one unique value that my function approaches to at this point. This means that the function limit at 3 does not exist. Similarly, let's see what happens with this function. We need to graph first. I use GeoGebra. And now let's observe what happens as we approach to 0 from the right-hand side. As you see, my function values will decrease with no bound. That means that our right-hand limit can be equal to -infinity. Similarly to the left-hand side, as we approach to 0 from the left, our function values will decrease with no bound. Therefore, our left-hand limit is also -infinity. We can also support this with a table of values. Here we go. We can notice from the function values that as we approach to 0 from the left, we approach to infinity on the y-axis. Similarly, on the right-hand side, as we approach to 0 on the x, we approach to -infinity on the y-axis. This means that technically we don't have a limit at 0. The limit, the two-sided limit, does not exist. However, since both the one-sided limits were equal, we can describe this behavior at 0 as it approaches -infinity. And now it is your time to practice. Please pause the video and press continue once you have your answers. And here are the answers. And the piecewise defined functions graph is here. You can see that the one-sided limits are not equal, so we don't have a two-sided limit. There is a special behavior where we can state that the limit does not exist, and that's the oscillating behavior. If you graph this function, cosine 1 over x, you will get a graph like this. As we are approaching to 0, as you see, it's getting more and more dense. However, the function still oscillates between -1 and +1. So therefore, as we are approaching to 0, we can say that our limit does not exist. And with this, we have finished our first learning objective. Now let's talk about limits at infinity. In case x increases without a bound, and the fx values approach to a unique value L1, we say that the function has a limit at infinity and it is L1. Similarly, in case x decreases with no bound and the fx values approach to a unique value L2, then we can say that the function has a limit at negative infinity and that value is L2. How can we connect the asymptotes to all this? Let's see the vertical asymptote first. In case we have a limit at point C and it's positive or negative infinity, we can say that x equals C is a vertical asymptote of the graph of fx. This limit at point C could be a one-sided limit, it doesn't matter which one, or even a two-sided limit. The horizontal asymptote, in case my function has a limit at positive or negative infinity, and that limit is C, then we will say that the y equals C line is a horizontal asymptote of the graph of fx. Now let's see two more examples to find the limits at infinity. First of all, we need to graph the functions, of course, and then we will observe what happens with the first function as x decreases with no bound. Now, x decreases, so we're looking at the left direction. Let's see what happens with the function values. Here we go. It will get closer and closer to 0. So this means our limit at negative infinity will be equal to 0. Let's see what happens with the other graph. Dot the graph first. This is what we get. And now we will approach positive infinity. So this means we're increasing x's with no bound. What happens? What happens with the function? Well, this is the way it goes. And we see it's getting closer and closer and closer to a number, which is this line here. We just simply need to read off the graph which number is this. We can see it's -3. So we say the limit at positive infinity is -3. And now it is your time to practice. Please pause the video and press continue once you're ready with your answers. And here are the answers. And in this last question, as we increase x with no bound, we can observe oscillating behavior. So this means this limit does not exist.